Hello class, in this video we cover section 11.6. From the title of this section, now we can see we have three topics to cover, to study in this section. Probability of events involving not, probability of events involving or, and the concept of us. So three things in this section. First thing, complement. What's the definition of a complement? Complement of an event is the event not E. Okay? Complement of event E refers to the event that not occurring. We have learned negation in chapter 3, right? Yeah, we learned negation in chapter 3. I think we also have complement in chapter 2, set theory. In chapter 2, remember, if we have the universal set, the rectangle universal set, if this is A, then A prime would be the region represented by the shaded region, right? The shaded region in the box, but outside the circle A. So the shaded region is A prime. Remember, events are subsets of sample space, so they are very consistent, And we also use A prime to represent the complement of event A. Then what's the relationship between probability of A and the probability of A prime? Again, A prime here is the complement of A, means A not occurring. So this is the relationship between them. P of A plus P of A prime, or sometimes we use A bar to represent A not occurring, equals 1. Let's say the chance or probability of raining tomorrow is 20%. Then what's the probability of tomorrow not raining? You would say 80%, right? Because 20% plus 80% is 100%. Exactly. If two events are complement of each other, then their probabilities add up to 1. 1 is 100%. Because with region A, look at the Venn diagram, with region A and region A prime, together they make the whole universal set. The universal set here refers to the sample space. The probability of sample space occurring is 1, is 100%, is certain to occur. All right, let me repeat. The first topic, complement of an event, refers to an event that the event E, let's use E, not occurring. We either use this to represent the complement, or use prime, or use bar. Those are the notation for the complement of an event. And if the two events are complements of each other, then their probabilities must add up to 1. Let's look at the examples. We are talking about deck of cards here. And you are dealt 1 card from a 52 card deck. So this sentence, the first sentence, tells us the experiment or your task. Randomly select 1 card from the 52 card deck. We need to find the probability that you are not dealt. So keywords not. So we are looking for the probability of complement, right, of the following events. So since P of A bar, sometimes I use this notation, or sometimes I use the other notation. Probability of the complement of A equals 1 minus probability of A. If finding probability of A is easier than directly finding the probability of A bar, then we should use this formula. We should use this formula to find the probability of complement. Yeah, we find the probability of A and then subtract the probability of A from 1 to get a probability of A bar. So this would be the case. This example would be the case. We are looking for probability that you are not dealt a club. How about let A be the event that you dealt a club? Then probability of A is not difficult to find, right? Yeah. So club. So we have 4 suits. 4 suits. You know, this part A. We can see the sample space as 4 suits, right? Hearts, clubs, diamonds, spades, and it's classical because each suit has 13 cards. So each suit has the same chance to occur. So this is classical. Then the sample space has 4 possible outcomes, and event A is to get a club card. Club card, so that is 1/4, right? Does that make sense? Even you consider the whole sample space is 52 cards, then among the 52 cards you have 13 clubs. 13/52 still give you 1/4. Yeah, either way is correct. Then P of A bar, the probability that you are not dealt a club would be 1 minus P of A. Use 1 to minus the probability you just got. 1 minus 1/4 gives you 3/4. I apologize again because my surface is broken. It doesn't really let me, certain part of the board doesn't really let me write anything. So 3/4, 75%. Okay, that's part 1. Let me label it. Part 2, we are looking for the probability that you are not dealt a red picture card. How about let B be the event that you are dealt a red picture card. Then let's see what is the probability of B. And this time we are going to consider all the 52 cards as a sample space. So the denominator is 52. Among the 52 cards, how many of them are red picture cards? Let's look at the photo here. Among the 52 cards, how many of them are red picture? Hold on, let me fix that. Okay, so we have half of them, 26 cards are red, right? So 2 suits are red, hearts and diamonds. And hearts, we have 2 red cards. Hearts, we have 3 picture cards. And diamonds, we have 3 picture cards. So in total, we have 6 red picture cards. So numerator is supposed to be 6. All right, because we have each suit has 3 picture cards. In total, we have 12 picture cards. Half of them are red, half of them black. So the total number of red picture cards are 6. Reduce this fraction. Divide the numerator by 2, we have 3. Divide the denominator by 2, we have 26. So that's the probability of B, right? Yeah, getting a red picture card. Then what's the probability not getting a red picture card? What's the complement? Use 1 to minus 3/26. Yeah, you can try use the TI-84 calculator. It's gonna help you plenty. If you manually calculate, that's also important. We can write 1 as 26/26 and minus 3/26. And we're gonna keep the denominator 26 and solve the numerator. 26 minus 3 is 23. 23 is odd. 23 is prime, and 23 is prime. 26 is not divisible by 23, so this is already simplified. Answer is 23/26. All right. So that's the first topic, complement. I think it's pretty straightforward. The second topic of this section is about probability of one event or the second event. If we consider two events, A and B, P, A, or B, that's what we're trying to figure out. All right, that's what we're trying to figure out. What's the probability of A or B? Suppose we know the probability of A and the probability of B. So we have two cases here. Recall the set theory. Consider A and B are sets. They are actually sets, right? They are subsets of the subsets of the sample space. You can see the sample space as a universal set. Let's say this is A, this is B. When the two sets are disjoint, when the two sets have no common members, we say the two sets are disjoint, right? Yeah, but when A and B are two events and they are disjoint, they have no common member, we say the two events are mutually exclusive. Mutually exclusive. Let me write down the words. We'll highlight here. Yeah, or mutually exclusive. So two sets are disjoint. If the two sets are events, then the two sets are disjoints actually refer to two events that are mutually exclusive. The formal definition for two events that are mutually exclusive is if the two events not possible to occur simultaneously. Okay, if A occurred, then B cannot occur. If B occurred, then A cannot occur. Then we say the two events are mutually exclusive. If it is impossible for events A and B to occur simultaneously, we say the two events are mutually exclusive. Use the Venn diagram to demonstrate the relationship of A and B. You would see two sets that are disjoint. The second point here is bulletin says the event A and A prime are actually mutually exclusive. Yes, if we look at A and A prime, A is this black circle, A prime is the region outside the black circle. As sets, they are disjoint, right? As sets, they are disjoint. As events, they are mutually exclusive. Of course, A and A prime means A not occurring. Feel the meaning. Of course, they are not able to occur at the same time, right? Okay, very straightforward. Then, under the condition that the two events A and B are mutually exclusive, the formula to find the probability of A or B is this formula. If A and B are mutually exclusive, then P of A or B equals P of A plus P of B. Very straightforward. This is also called the addition rule. The first formula of the addition rule. First formula of addition rule. We use addition rule to find the probability of A or B. Or here is inclusive or. Same with the set theory. A or B or both, right? And what if the two events are not mutually exclusive? A regular case. Let me draw the Venn diagram in which demonstrating two events and they are not mutually exclusive. They have overlapping part, right? Yeah, they are not disjoint. They're not disjoint. They have common parts. Then how should we find the probability of A or B? You might remember in set theory chapter 2, we have this formula. We have this formula. N of A union B equals N of A plus N of B minus N of A and B. N here is the cardinal number of the set. So if we change N to P probability, we would have the formula to compute the probability of any two events, the probability of A or B. A, B are any two events. They don't have to be exclusive. So P of A or B would be P of A plus P of B and then minus P of A and B. Okay, the meaning would be the same with the cardinal number, because the probability, if we look at a Venn diagram, the probability is proportional with the area of the set, right? And the area of the set also is proportional with the cardinal number of the set, or related to cardinal number of the set. So that's the formula we need to use to compute A or B, probability of A or B. So the process of finding probability of A or B is this. Firstly, you need to determine are A and B mutually exclusive or not. You need to understand what is mutually exclusive, right? Disjoint, no common member, not possible to occur at the same time or simultaneously. If A and B are mutually exclusive, use this formula to find the P of A or B. If they are not mutually exclusive, then it's more complicated. You have to use this formula to find the probability. You need to memorize the two formulas, okay? Once you understand, it's not difficult to memorize, to be honest. You don't really need to memorize by rote. All it takes is understanding it. Think about set theory, cardinal number. Let's practice. Let's practice. This is about a deck of cards again. You randomly select one card from a 52 card deck. The first sentence tells us what is the experiment, right? What the experiment is, what's the task. Select one from 52 cards. We need to find the following probability. Okay? The probability of getting a 7 or an 8. So you can write properly using notations, also very important for you to solve a probability problem. This is what I do. P of 7 or 8. In this context, it will not incur any confusion. It's pretty clear. 7, I use 7 to represent the event that I get a number 7. I use 8 to represent the event that I get a number 8, right? Since both of the two events only involve numbers, I'm going to consider the sample space as 1, 2, 3, 4, 5, 6, 7, all the way to 13, okay? We talked about this in previous section. Properly choosing sample space can make our calculation easier. Yeah, you can switch back and forth. So in this part 8, in this example, I'm going to use that as a sample space. All the 13 events are equally probable. Okay, so remember, whenever we need to find the probability of A or B, we need to consider, are those two events mutually exclusive or not? Think about, is that possible for the one card you draw to be number 7 and number 8 simultaneously? Is that possible? No. So the two events are mutually exclusive. Under the condition that the two events are mutually exclusive, P of 7 or 8 equals P of 7 plus P of 8. Sometimes they do this. They put a that to differentiate this event from just the number 7, right? Or number 8. Yeah, either way is fine, as long as you are not confused, you are clear. Then what's the probability of getting number 7? What's the probability of getting number 7? You have 13 numbers, right? 1 over 13, of course. And what's the probability of getting number 8? Another 1 over 13, right? Add them together, 2 over 13. And that's it. That's it. Number 2, you randomly select one card from a 52 card deck. find the probability of selecting a red 7 or a black 8. So those two events involve colors. So the original sample space doesn't work anymore. This time we're going to consider all the 52 cards as the sample space. They all have 1 over 52, that many, that chance to be drawn. Okay, we are looking for probability of getting a red 7. Yeah, depends on how you write that. Red 7 or black 8 is a word problem. Then we need to determine, are those two events mutually exclusive or not? Mutually exclusive or not. So I recommend you write it down on your scratch paper like earlier. I should have read it. Mutually exclusive. Write it down. Write it down. Okay. So what about this? In this case, red 7 and black 8, they are still mutually exclusive because you only draw one card, and only the one card not possible to be red 7 and black 8 at the same time. So they are mutually exclusive. And in the condition that they are mutually exclusive, we have P of red 7 plus P of black 8. And what's the probability of draw a red 7? And in this case, the sample space contains 52 cards in total, right? So the denominator is always going to be 52. How many red 7 do we have? Look at the picture. How many red 7 do we have? We have 2 of them. It's very tiny. This is a red 7. And we get another red 7, right? Red heart and red diamonds. So 2. And how many black 8 do we have? We also have 2 black 8. One is the club. A is black. The other is spades. Huh? It doesn't let me draw. Let me see what happened. 2 here, yeah. And then we add them up. 4 over 52. Simple fraction calculation. And divide 4 by 4. We have a 1. Divide 52 by 4, we have 13. Okay, we have 13. So the result is 1 over 13. Next, the next problem is not about the deck of cards anymore. It's about the spinner. It is equally probable that the pointer on the spinner shown will land on any one of the 8 regions, numbered 1 through 8. If the pointer lands on a borderline, spin again. Find the probability that the pointer will stop on. Let me see if I can change the to the next page. Erase those. Delete those. Okay, it's still number 4. Okay, I didn't really do anything, right? Okay, never mind. So let's just process this here. Let's find a sample space here. The sample space is region 1, 2, 3, 4, 5, 6, 7, 8. Classical because they are equally probable. Please do not use this sample space. Yellow, white, green, blue. No. That way, the sample space, the experiment is not classical model. You will end up a wrong answer. This has nothing to do with the color so far, all right? So we use the number because this gives us a classical model. We are looking for the probability of getting an odd number or a number greater than 3. So this is where we're going to find probability getting an odd number or number greater than 7, bigger than 3. All right, so let's consider the 2 events. Getting an odd number getting a number greater than 3. Are they mutually exclusive? A number greater than 3 include 4, 5. 5 is odd, right? So obviously they are not mutually exclusive. So on your scratch paper, you want to write this: not exclusive, not mutually exclusive. Yep, make that very clear. Not mutually exclusive. If they are not mutually exclusive, then we're gonna use another formula to represent the probability of odd or greater than 3, right? Yeah. So we have a P of odd plus P of greater than 3 minus P of, let me see if I can, sorry about that. My part of my board cannot be used right here, minus P of odd and greater than 3. So that's my notation. I think it's pretty clear to me. If it's not clear to you, then what you can do is let this be A, let this be B. Then P of A or B equals P of A plus P of B minus P of A and B. If that's easier for you, that's even better, okay? And next time we can use that notation. Then what is the probability of A getting an odd number? Among the 8 regions, how many of them are odd? 1, 3, 5, 7, 4. Half of them, right? Then that's 4 over 8. Probability of A. Probability of B. What's the probability of getting a number greater than 3? Denominator is still 8. How many of them greater than 3? From 4, right? 1, 2, 3, 4, 5. 5 over 8. And minus probability of odd and bigger than 3. So the denominator stays as 8. Denominator stays as 8. And numerator is how many of the 8 regions are odd and bigger than 3. Let's see. Bigger than 3 and odd. So we have this 5, this is 7. Five and 7, so 2 of them, right? Yeah, bigger than 3 and odd, so 2 of them. So we have 2 here. Okay, so do the math. Process those fractions. Keep the denominator 8. Numerator is 4 plus 5 minus 2. 9 minus 2, 7. So the answer is 7 over 8. I apologize now, it's not very reacting, so I'll just write the answer as that. Okay? 4 plus 5 is 9. 9 minus 2 is 7. The answer is 7 over 8. Part B. What's the probability of getting an even number or a number less than 4? So this time we are going to use A and B, okay? Make it easier for us. Let me erase those 2 things, 2 bubbles. Let me see if I close and reopen will fix the problem. This is 11.6. Where is it? 11.6 right here. We were here, right? 2, and then we have 7 over 8. Part B. Finding the probability of getting an even number. Let's use A to be the result that getting an even number. Or getting a number less than 4. And we use B to represent getting a number less than 4. And we are looking for P of A or B. P of A or B. Again, we need to determine all the time, always determine are the 2 events mutually exclusive or not. What do you think? Not. They are not mutually exclusive. Okay, so on our scratch paper, Write it down, not mutually exclusive. Then we use the second formula. P of A or B equals P of A plus P of B minus P of A and B. What's the probability of P of A? What's P of A? A region getting an even number, so half, right? What's the probability of B? A region get a number less than 4, so 1, 2, 3, 3. And P of A and B, denominator remains as 8. Numerator, how many of the 8 regions are even and less than 4? Strictly less than 4. 1, because only 2, right? 1. So you can calculate that. Keep the denominator as 8. Numerator is 4 plus 3 is 7. 7 minus 1 is 6. 6 over 8 reduces 3 over 4. That's the result. All right. So next question. So this is a picture. Okay. Move this picture down. See if I can do that. Yeah. So next question is based on this table. So far, all the probability problems are classical. And when you see a table like this, you know, okay, it's going to be an empirical problem. The table above shows the educational attainment of the U.S. population ages 25 and over. In 2020, use the data in the table expressed in millions to solve the following. Okay, so let's see. A, not completed the 4 years of high school. Okay, so not completed. The event seems a complement, right? Yeah, event seems a complement, not complete the 4 years of high school. Are we gonna choose using this formula to find the probability? Depends. We are not going to use it for this case. Let me explain why. Because it's very easy to make a mistake. I need to make the pointed out very clearly. Not a completed 4-year high school refers to this category. The complement of that is not this category. Okay, they are not complement. The first two categories, they are not complement. In fact, the complement of the yellow part of the first category is the entire rest 3 categories. So we're gonna not finding the probability of this one, and instead of finding the probability of this one and use 1 to minus that. That is a longer route. We are not going to take that route. All right. So simply means you must read the question carefully. Not completed the 4 years of high school simply means the probability of randomly select the person belong to this category. Less than high school, 4-year high school education. How many people there? 35. And total people is 156. So by the empirical probability, we have 35 over 156. That's the total, right? Yeah. How do we keep the result? 5/7. It's not reducible. So as a fraction, this is good enough. 35 is 5 times 7. 156 is not divisible by 5, is not divisible by 7 either. So as a fraction, this is good enough. Or the problem might want you to convert to decimal, then you just do so. Part B, completed less than 4 years high school or 4 years of high school only. Okay. Randomly select a person it completes less than 4-year high school or four-year of high school only, right? So we are looking for P of A or B. When we look for probability of A or B, always start from what? Determine mutually exclusive or not. This is a mutually exclusive because if a person finished 4-year high school, then it's not going to be A. If the person not finished 4-year high school yet, then it's not going to be B. A and B are not possible to occur at the same time, so they are mutually exclusive. Since A and B are mutually exclusive, P of A or B would be equal to P of A plus P of B. Today's my computer is very slow. Reaction. P of A plus P of B. And what is the probability of A? Complete less than 4 years of high school. Didn't we just got a value earlier? 35 over 156, right? And what's the probability of getting 4-year high school only? That's the second category. Let's go up to the picture. So 52 over 156. 52. 52. Add them up. We have 87 as the numerator, 156 as denominator. Let's see if we can simplify 87 divided by 156. Now you will appreciate the benefit of the calculator. 57 is divided by 3. 156 also divides by 3. How do we know if a number divides by 3? Let's take 57 as an example. 87 as example. 87. So 8 and 7 add up to 15. 15 is divided by 3. So 87 is divided by 3. Divided 87 by 3, we have 29. And how do we know if the denominator divisible by 3? 1, 5, 6, 3 digits, right? They add up to 12, and 12 is divisible by 3. So 156 is also divisible by 3. Divide 156 by 3, we have 52. So 29 over 52, that's reduced. Or you can use a calculator to double check. And really appreciate the benefit of TID for calculator. Part C, find the probability of completing 4 years of high school only, or is a woman. So this time we let complete 4 years only as A. Randomly select the person is a woman as B. Then P of A or B. In this case, of course, in each part, A and B refer to 2 different events, right? You're going to be aware of that. And they are not mutually exclusive because a woman could be any educational category, right? Not mutually exclusive. Not mutually exclusive. So P of A or B equals P of A plus P of B minus P of A and B. What is the P of A? Complete 4 years only. Yeah, we had that result from part B, 52 over 156. And what's the probability of finding randomly select a person that is a woman? The denominator going to remain as 156, right? A woman, 80. Among the 156 million people surveyed, 80 million are female, so 80 is the numerator. Minus the probability of A and B. Randomly select the person, and the person is a woman, and high school only, right? Yeah, let's see. Let's do this. Let's do this. Female, high school only. Did you see that? Where did they intersect at? 28, right? So the numerator is going to be 28. So let's plug in here, 28. And now I'll leave you to complete the calculation part. So that is the second topic of this section. Or, let me summarize quickly. To find the probability of A or B, first thing you need to do is to determine, are A, B mutually exclusive or not? If they are mutually exclusive, then P of A or B equals the sum of the probabilities of the two events. Otherwise, if they are not mutually exclusive, then you're going to use this formula, the longer version formula, to find the probability of A or B. Okay? You need to know both. You need to remember both formulas. Together, the two formulas gives us the addition rule in probability theory. The last topic of this section is about the odds. We have two formulas. Okay, this one and this one. The odds of an event, the odds for event, or the odds favor. Yeah, so this notation represents the odds of favoring event A occurring is a ratio. So after you understand the definition of odds, you should see the difference between the concepts. Odds and the probability, two different definitions. They are very closely related, but there are two different concepts. Probability is a number between 0 and 1. The number cannot be negative, 0 is fine, cannot go beyond 1. Is a value, one value. But odds is a ratio. You know how many ways we can represent a ratio? Let's say 1 to 2. We can do this, or 1 to 2, or 1 to 2. Yeah, we have different ways to represent a ratio, right? Same with odds. We use fraction more often in this book. So very important, knowing odds is not one value, is a ratio. Yes, your result might be just 1 over 2, but it's technically not a number, it's a ratio, 1 to 2. And the odds of against event E occurring is the reciprocal of the odds favoring event A occurring. So once we start to process the examples, you can understand how do we find the odds favoring an event, and how do we find the odds of against an event occurring very quickly. Let me show you this example. One card is randomly selected from a deck of cards. Find the odds in favor. Okay, let's highlight this information. In favor of which event? I'm going to let this event be A. Yeah, I like to use A, B, C better than E. Okay, then what is the probability of A? So whenever you need to find the odds of an event, you need to find the probability of the event and the probability of the complement of the event. So if we let A be drawing a picture card, among the 52 cards, how many picture cards? 12. We have been using the picture with the deck of cards many times, right? Yeah, you should remember, among the 52 cards, we have 4 suits. Each suit has 3 picture cards: Joker, Queen, and King. And 4 suits, 3 times 4, 12. 12 picture cards in total. So the probability of drawing a card, and the card is a picture card, is 12 over 52. If we reduce it, divided by 2, we have 6 over 26. Actually, we should divide by 4. GCF is 4. Divide 12 by 4, we have 3. Divide 52 by 4, we have 13. So 3 over 13. And what is the probability of A bar or A prime, the complement of A, P of not A, would be 1 minus 3 over 13. You remember this, right? 10 over 13. All right, so let's find the odds. The odds of favoring A, that's the notation. Sometimes I just write the words down. The odds of favoring A would be, I think the reason is because all those writings are treated as a picture. So equals P of A over P of A bar. So numerator P of A is 3 over 13. Denominator P of A bar is 10 over 13. So the ratio is 3 to 10. Or you can just do 3 to 10 this way, right? Yeah, either way is fine. Again, even the result looks like a fraction, but you need to understand the odds is a ratio, 3 to 10. The result is 3 to 10. The odds in favor of event A is 3 to 10. Okay, part B. Part B. What's the odds of favoring drawing a black card? I'll let this be event B, okay? Event B, black card, happen to be B as the initial black. Then probability of B. We only have 52 cards in total. Half of them are black, half of them are red. Evenly, right? So 1 over 2. Probability of drawing a black card is 1 over 2. Then probability of not drawing a black card, the complement, is also 1 over 2 because 1 minus 1 over 2 is 1 over 2, right? Then what's the odds of in favor B? It's gonna be P of B over P of B prime, or complement of B. So that would be 1 over 2 over 1 over 2, and is 1 to 1. Yeah, the result could be just 1. Depends on how does the question require you to represent the result. But you need to know, again, is a ratio. Part C, the odds against drawing a red jack. Red jack. Let me use C. How about use C to represent the event getting a red jack? Let's find out what is the probability of C and what's the probability of not C. We have 52 cards. How many of them are red jack? Each suit has 1 jack only. So we have 4 jacks in total. 2 of them are red, 2 of them are black. So 2 red jacks. And reduce the fraction 1 over 26. And the probability of the complement of C would be 1 minus 1 over 26, 25 over 26. And the odds of against, okay, against, knowing the notation, the odds of against C occurring would be, this time very, very important. You're going to remember the numerator is going to be P of C bar. Denominator is P of C. Do you see the difference? Odds of favoring and odds of against depends on favoring or against. The numerator and the denominator has different order, right? In this case, is against, so the numerator is a P of C not occurring, 25 over 26. And denominator P C occurring is 1 over 26. So we have 25 to 1, or 25 over 1. The result is 25 over 1 or 25 to 1 is a ratio. It's a ratio. Yeah, very, very important. After we learn the third topic of this section, odds, at least please know it's different from probability. Probability is one number. The number is bigger than or equal to 0, less than or equal to 1, representing the chance of a specific event occurring. But odds is a ratio. Yeah. Recall in middle school, how do you learn ratio? Ratio has so many different ways to be represented, right? Is a ratio. It actually technically involves two numbers, one on the top, one on the bottom. So that's all the three topics of this section. Please study and watch the video and work on your assignments. Feel free to email me if you have any questions. I'll see you in the next video. Bye bye.